All right, let's get into it. Today, we are going to be chemical detectives. We're cracking a code that stumped the greatest minds in chemistry for years, a revolutionary idea called Werner's coordination theory. So picture this. It's the late 1800s. You're a chemist and you see these bizarre, really colorful compounds. Things like cobalt chloride mixed with ammonia molecules. And the rulebook, well, the rulebook just gets thrown out the window. None of the normal rules of chemistry could explain how they were built. How on earth could a stable metal like cobalt suddenly grab on to so many other things? It was a huge puzzle. And then, in 1893, this guy, Alfred Werner, has a moment of pure genius. He comes up with this totally bold, totally new idea that changed everything we thought we knew about chemical bonds. He's called the father of coordination chemistry for a reason, and his theory is exactly what we're going to break down today.
So, what was this big idea? Well, Werner said, what if metals don't just have one way of bonding? What if they have two? He called them primary and secondary valencies. And this, right here, is the heart of his entire theory.
Okay, first up, we've got the primary valency. Now, this one is pretty easy to wrap your head around. It's simply the positive charge on that metal ion, smack in the middle. We now call this its oxidation state. Just think of it as the main electrical charge that needs to be balanced out. But then we have the secondary valency, and this was the real game changer. This is the number of groups, molecules, or ions that are literally stuck directly to the metal. They form this tight little unit. Today, we call that the coordination number. It's all about who is physically attached to that central atom. And this is where it gets really interesting. Let's look at the differences. The primary valency, those bonds are ionizable, meaning they can break apart and float away in water. But the secondary valency? No way. Those bonds are strong, they're non-ionizable, and they're directional. They point in very specific directions. Here are a couple little memory tricks for you. Primary valency is for the positive charge, and secondary valency is for the spatial structure.
Okay, I just used a super important word there, directional. If these secondary bonds point in specific directions, what does that actually mean? I mean, what's their real job?
It determines the shape, the geometry of the whole thing. Because those bonds are locked into place, they give the entire complex a unique 3D structure. This idea is the key to, well, pretty much everything else. All right, so here's a fun little brain teaser. We've got one type of bond for charge and another for structure, but is it possible for one single little ion to do both jobs at the exact same time? Yep, it absolutely can. An anion, like a chloride ion, is the ultimate multitasker. It's got a negative charge, right? So it can balance out the metal's positive primary valency. And it can also stick directly to the metal to help satisfy that secondary valency. It's literally doing two things at once. So a theory is just a cool story until you can prove it. Werner couldn't actually see these atoms, so he had to get clever. He designed this brilliant, simple experiment to prove his two-valency model was the real deal. He needed cold, hard facts. And here's exactly how he did it. It's a simple three-step recipe for discovery. Step 1, dissolve the colorful compound in water. Step 2, add some silver nitrate. And step 3, carefully collect and measure the white solid stuff, the silver chloride that forms. Now here is the secret sauce. This test is a very clever trick. The silver nitrate can only see and react with the chloride ions that are satisfying the primary valency, the ones that are just floating around on the outside. It totally ignores the chlorides that are locked up tight inside the complex. All right, it's our turn. Let's put on our detective hats and solve a case using Werner's own method. We've got a compound, COCl3.5NH3. We run the test, and we get 2 moles of that silver chloride precipitate. So, what's the real structure? This is our one and only clue. But trust me, it's all we need. 2 moles of precipitate. That one number tells us everything. So, deduction number 1. It's pretty straightforward. If we got 2 moles of silver chloride, it means there have to be 2 free-floating chloride ions. These 2 guys are outside the main structure, just balancing the charge. Okay, let's move on to our second deduction. We know from all his experiments that cobalt's secondary valency, its magic number, is 6. Now, we've got 5 ammonia molecules inside already. To get to 6, well, we need one more thing,
and that has to be our third chloride ion. It must be inside the sphere.
And there you have it. We put it all together. 5 ammonias and 1 chloride are inside those brackets, making up the secondary valency of 6. The other 2 chlorides are outside, taking care of the primary valency. Case closed. We solved it. Okay, let's try one more. This one's a little different. Say we have a platinum complex, and we test it and find out it's a non-electrolyte. That means when you dissolve it, it produces 0 free ions. Zilch. What does its formula have to be?
Well, if there are no ions on the outside, then everything must be on the inside. It's the only logical answer. All 4 chlorides and both ammonias are huddled together, tightly bound to that platinum in the middle. Nothing can break away.
Now, Werner's theory did more than just explain formulas on a page. Its greatest achievement, its lasting legacy, was in revealing the hidden 3D world of molecules. It gave us geometry, and it gave us isomers. This right here is the biggest takeaway of the whole explainer. Isomers are molecules that have the exact same chemical formula, but the atoms are arranged differently. And they can only exist because the bonds holding them together, those secondary valencies, are locked into specific directions. And this isn't just an abstract idea. It explains stuff we can actually see. The compound COCl3, 4NH3, can be either violet or green. Why? Because they're geometrical isomers. In one, the chlorides are next to each other, and in the other, they're on opposite sides. Same atoms, different arrangement, different color. How cool is that? Now, as incredible as it was, Werner's theory wasn't the end of the story. It was a structural model. It was amazing, but it couldn't explain why these things have color or why some of them are magnetic. For those answers, we'd have to wait for new theories that looked at the electrons themselves. Okay, you have soaked up a ton of information. Let's do a quick rapid-fire recap to make sure the biggest ideas are locked in. I'll ask a question, you think of the answer. Ready?
First one, that primary valency, what do we call it today?
The oxidation state. You got it. It's all about that charge. All right, next up, that revolutionary secondary valency. What does it determine? The geometry, the 3D shape. Perfect. And the big one, the most important idea of them all. Why is it even possible for isomers to exist in the first place? Because those secondary valencies are directional. They are fixed in space. If you remember only one thing from today, let it be that. And that kind of leaves us with one final amazing thought. It's just incredible, isn't it, how a simple idea that metals have 2 different ways of bonding could unlock our entire understanding of the 3D structure of so much of the chemical world. And that's all for this explainer. Thank you so much for joining us. We really hope you enjoyed cracking the code with us, and we'd love to invite you to our next lesson in John Lowy memory.